Every generation grows up believing that the impossible is simply waiting for the right invention. Once, people believed humans would never fly. Then the Wright brothers changed history. They said no machine could outrun the speed of sound, until Chuck Yeager shattered that barrier. Time and again, humanity has turned impossibility into reality. So it's only natural to ask the next question. If we've conquered the skies, if we've walked on the moon, if we've sent machines beyond the edge of our solar system, then why shouldn't we one day build a starship capable of crossing the galaxy in days instead of thousands of years? For decades, science fiction has promised us exactly that. A single command. Engage! Stars stretch into brilliant lines of light. Space bends around the ship. Entire galaxies become weekend destinations. Civilizations separated by thousands of light years suddenly feel like neighboring cities. It's one of the most captivating ideas ever imagined. The warp drive. As someone who has spent a lifetime exploring the deepest questions in theoretical physics, questions about space-time, extra dimensions, quantum reality, and the hidden architecture of the universe, I understand why this idea refuses to disappear. I want it to be true just as much as anyone else. Because if warp drive were possible, it wouldn't simply revolutionize transportation. It would redefine humanity's future. It would transform us from a civilization trapped around a single star into one capable of exploring an entire galaxy. But physics isn't interested in what we want. Physics only cares about what nature allows. And after decades of studying Einstein's theories, quantum mechanics, and the extraordinary mathematics behind spacetime itself, I've come to a conclusion that many people don't want to hear. Warp drive will almost certainly never work. That's an extraordinary statement. Not because engineers aren't clever enough. Not because we lack powerful computers. Not because our technology is primitive. Those problems can always be solved. History has taught us never to underestimate human ingenuity. The real obstacle lies somewhere much deeper. The problem isn't engineering. The problem is reality itself. The laws that govern our universe appear to reject the very idea of faster-than-light travel. And the more physicists investigate warp drives, the more nature seems to close every possible escape route. What's fascinating is that this conclusion wasn't obvious at first. In fact, for a brief moment during the 1990s, it seemed as though Einstein himself had accidentally left a loophole hidden inside his own theory. A loophole that could allow humanity to cross the stars without ever breaking the cosmic speed limit. That possibility electrified the scientific community. Newspapers called it the real science behind Star Trek. Researchers began asking questions that had previously belonged only in science fiction. Could space-time itself become the engine? Could the universe be persuaded to carry us instead of forcing us to travel through it? For a while, the mathematics seemed almost miraculous. But then physicists kept asking more questions. And each answer revealed a new obstacle. An obstacle more fundamental than the one before it. Until eventually an astonishing pattern began to emerge. It wasn't just one problem. It wasn't even two. Every branch of modern physics seemed to be independently reaching exactly the same conclusion. General relativity objected. Quantum mechanics objected. Energy conservation objected. Causality objected. Even our best attempts at quantum gravity appear to object. It's almost as though the universe has built multiple security systems around one simple rule. You may explore. You may discover. But you may never outrun light. To understand why, we first have to understand the problem warp drive was invented to solve. Because without that problem, warp drive would never have been imagined in the first place. Stand outside on a clear night. Look toward the stars. From Earth, they seem peaceful, close together, almost intimate. Thousands of tiny lights scattered across a dark sky. Our eyes trick us into believing the universe is somehow compact, manageable. But nothing could be further from the truth. The nearest star beyond our Sun is Proxima Centauri. Its light takes more than 4 years to reach us. That means every time you look at it, you're seeing light that left before an entire presidential term had even finished. And Proxima Centauri is practically our next-door neighbor. Beyond it lie billions upon billions of stars separated by distances so enormous that human intuition completely fails to grasp them. Light travels at nearly 300,000 kilometers every second, fast enough to circle Earth more than 7 times in a single second. Nothing we have ever built comes remotely close. Our fastest spacecraft, the Parker Solar Probe, reaches astonishing speeds while diving toward the Sun. Yet even at those incredible velocities, reaching Proxima Centauri would still require thousands of years. Not decades. Not centuries. Thousands of years. A civilization could rise, disappear, and become ancient history before the spacecraft even arrived. Suddenly, the dream of exploring the galaxy begins to look impossible. Not because space is hostile, but because it is unimaginably vast. And that realization creates one unavoidable question. If nothing can travel faster than light, how could any civilization ever become truly interstellar? That question haunted scientists for generations. Then, in 1994, a young Mexican physicist named Miguel Alcubierre asked a question so unconventional that it changed the conversation forever. He wasn't trying to build a faster engine. He wasn't trying to accelerate a spacecraft beyond light speed. Instead, he wondered something much stranger. What if the spacecraft never moved through space at all? What if the spacecraft never moved through space at all? At first, that sounds like nothing more than clever wordplay. Every journey, after all, requires movement. If you want to travel from New York to Tokyo, you have to cross the Pacific. If you want to reach Mars, you have to traverse millions of kilometers of empty space. Motion seems unavoidable. But Einstein's theory of general relativity quietly hides a remarkable truth. Space itself is not fixed. It isn't an invisible stage on which the universe performs. It is an active participant in the performance. Space can stretch. It can curve. It can twist. It can ripple like the surface of a pond after a stone is thrown into the water. We've already seen this happen. The universe has been expanding ever since the Big Bang. Every distant galaxy is being carried away, not because it is flying through space at impossible speeds, but because space itself is growing between galaxies. In fact, some galaxies are receding from us faster than the speed of light. That statement sounds impossible until you realize they're not violating Einstein's speed limit at all. They're simply writing the expansion of spacetime itself. And that single observation inspired one of the most fascinating ideas in theoretical physics. Miguel Alcubierre asked a simple but revolutionary question. If the universe can expand space, why couldn't we do it ourselves? Imagine standing on a moving walkway at an airport. You aren't running. You're simply standing still while the floor carries you forward. Now imagine replacing that moving walkway with spacetime itself. Instead of accelerating a spacecraft, you would compress space in front of it while expanding space behind it. Your destination would effectively move closer. The place you left would move farther away. The ship inside the bubble wouldn't technically be moving through space at all. Instead, space would be carrying the ship. The elegance of the idea was breathtaking. Inside the bubble, astronauts would feel perfectly normal. No crushing acceleration. No enormous g-forces. No violation of Einstein's rule that nothing can travel faster than light locally. From the crew's perspective, everything inside the bubble would remain calm and flat. Yet to observers outside, the bubble itself could cross unimaginable distances at what appeared to be many times the speed of light. For a moment, it looked like science fiction had become legitimate physics. And that's exactly why Alcubierre's paper became so famous. For the first time, faster-than-light travel wasn't being discussed by television writers or Hollywood directors. It was appearing in a respected scientific journal. The equations were real. The mathematics checked out. Every symbol obeyed Einstein's field equations. That distinction is incredibly important. Many people assume physicists immediately dismissed the idea. They didn't. Quite the opposite. Most physicists found it fascinating precisely because the mathematics was internally consistent. The equations themselves weren't broken. The geometry worked. On paper, the warp bubble existed. And that's where the excitement began. Newspapers quickly announced that Star Trek's warp drive had moved one step closer to reality. Science magazines published colorful illustrations of enormous spacetime bubbles carrying futuristic spacecraft across the galaxy. Researchers around the world started asking a question that had never before been taken seriously. Could humanity actually build one? For a few years, optimism spread far beyond the scientific community. If the mathematics allowed it, surely engineering would eventually catch up. After all, history is full of technologies that looked impossible before they became routine. There was a time when electricity seemed magical. There was a time when splitting the atom sounded absurd. There was even a time when computers filled entire buildings and possessed less power than the phone in your pocket today. Perhaps warp drive was simply another revolutionary technology waiting for its moment. But science has a habit of rewarding patience. The first answer is rarely the final answer. Once the excitement settled, physicists began examining the Alcubierre solution more carefully, not asking whether the equations were correct, but asking something much more important. Could nature actually build such a thing? Because mathematics and reality are not always the same. A beautiful equation doesn't guarantee a physical object. General relativity permits many strange geometries. Some solutions describe wormholes connecting distant regions of space. Others describe rotating universes where time itself loops backward. Some even permit theoretical time machines. The equations don't immediately forbid these bizarre possibilities. But that doesn't mean our universe allows them to exist. Physics isn't simply about writing equations. It's about discovering which equations describe reality. And that's where the first cracks began to appear. Creating a warp bubble required something that had never been observed in the form the theory demanded. Not enormous amounts of ordinary energy. Not antimatter. Not nuclear fusion. Something even stranger. Negative energy. At first glance, that phrase sounds almost meaningless. How can energy be negative? Everything we experience in everyday life seems to possess positive energy. A speeding train has kinetic energy. A stretched rubber band stores potential energy. Sunlight carries radiant energy across millions of kilometers. Every familiar form of energy adds to the universe. Negative energy appears to do the opposite. It behaves almost like a debt written into reality itself. And if warp drive were ever going to work, this impossible substance would have to exist in extraordinary quantities. This wasn't a minor engineering challenge. It became the first warning sign that the universe might not be as cooperative as the equations suggested. Physicists searched for examples of negative energy in nature. Surprisingly, they found one. Hidden deep inside quantum mechanics. It emerged from one of the strangest experiments ever performed. An experiment involving nothing more than two perfectly polished metal plates placed unimaginably close together. Between those plates, something extraordinary happens. Even empty space isn't truly empty. According to quantum mechanics, the vacuum constantly boils with invisible activity. Particles appear, disappear, then appear again in an endless microscopic dance. These virtual particles normally remain hidden from view. But when two conducting plates are brought incredibly close together, they restrict which quantum fluctuations can exist between them. Outside the plates, every fluctuation is allowed. Inside, many are forbidden. That tiny imbalance creates an equally tiny force, a phenomenon now known as the Casimir effect. It has been measured repeatedly in laboratories, and it provides one of the few known situations where a region of space behaves as though it possesses negative energy density. For warp drive enthusiasts, this discovery seemed incredibly encouraging. Negative energy wasn't just mathematical fantasy. Nature itself appeared capable of producing it. But excitement quickly gave way to disappointment, because the amount produced by the Casimir effect is almost unimaginably small. Not merely insufficient, astronomically insufficient. It would be like trying to power an entire civilization using the static electricity generated by rubbing a balloon against your sweater. The scale simply doesn't compare. And as physicists continued refining their calculations, the numbers became increasingly difficult to accept. Some early estimates suggested a functional warp bubble would require negative energy equivalent to the mass energy of an entire planet. Other calculations pushed the requirement toward the mass of our Sun. Even the most optimistic revisions still demanded energy far beyond anything humanity has ever produced, or even knows how to imagine producing. The deeper researchers looked, the more the dream of warp drive began transforming into something else. Not an engineering challenge, but a confrontation with the fundamental architecture of reality. And this was only the first obstacle. The next discovery would prove even more unsettling. Because even if someone somehow handed us all the negative energy in the universe, there was another problem waiting inside the warp bubble itself. Even if someone somehow handed humanity every ounce of negative energy we could ever need, the journey toward a functioning warp drive would still be far from over. In fact, this is the point where the story becomes truly astonishing. Because the next obstacle isn't about energy. It isn't about engineering. It isn't even about technology. It's about control. Imagine, just for a moment, that against all odds, you built the perfect warp ship. You somehow generated the impossible amount of exotic negative energy. The warp bubble forms exactly as Alcubierre's equations predicted. Every instrument on board confirms that the bubble is stable. The engines activate. Space compresses in front of the ship. Space expands behind it. The stars outside begin to distort. Within seconds, your spacecraft appears to be crossing interstellar distances that would normally take thousands of years. Everything seems perfect. Until you decide it's time to stop. That simple decision reveals one of the most devastating problems ever discovered. According to the original Alcubierre solution, the crew inside the warp bubble cannot control the bubble once it is formed. Think about that for a second. The people inside the spacecraft, the very people risking their lives on the mission, cannot steer. They cannot accelerate. They cannot slow down. They cannot switch the drive off. Why? Because of the strange way information behaves inside a faster-than-light warp bubble. Einstein's universe has one absolute rule that has survived every experimental test ever performed. Information cannot travel faster than light. Not messages. Not radio signals. Not commands. Nothing. This rule doesn't simply limit spacecraft. It limits cause and effect itself. If information could outrun light, the logical order of the universe would begin to collapse. Inside a warp bubble moving faster than light, a bizarre horizon forms around the spacecraft. It's remarkably similar to the event horizon surrounding a black hole. You've probably heard that nothing, not even light, can escape a black hole once it crosses the event horizon. The same basic idea appears inside a warp drive. The front edge of the warp bubble moves away faster than signals from the spacecraft can ever reach it. Imagine trying to shout instructions to someone running away faster than the speed of sound. Your voice will never catch up. Now replace sound with light. That's the problem physicists discovered. The engines responsible for shaping spacetime exist at the edge of the bubble. But every command issued from inside the spacecraft travels at light speed. The bubble itself is already moving faster. The commands never arrive. It's like sitting inside a car whose steering wheel is no longer connected to the wheels. You can turn it. You can push every button. You can slam on the brakes. Nothing happens. You're simply a passenger. Even worse, the original warp bubble would have to be programmed completely before the journey even began. Every destination, every course correction, every moment of acceleration, every moment of deceleration, everything would need to be calculated in advance. If an unexpected asteroid appeared, too bad. If another spacecraft crossed your path, nothing you could do. If your destination suddenly became unsafe, there would be no way to change course. You're trapped inside your own invention. For many researchers, this wasn't merely an inconvenience. It fundamentally challenged the usefulness of the entire concept. A spacecraft that cannot be controlled is hardly a spacecraft at all. But the problems didn't stop there. As theoretical physicists continued exploring the mathematics, another disturbing prediction emerged. The warp bubble wasn't simply carrying the spacecraft. It was interacting with every particle, every photon, and every fragment of radiation scattered throughout interstellar space. Remember, space isn't perfectly empty. Even the vast regions between stars contain hydrogen atoms, dust grains, cosmic rays, and high-energy particles moving in every direction. Normally, these particles are incredibly sparse. A conventional spacecraft encounters very few of them. But a warp bubble changes everything. As the bubble compresses space-time in front of the ship, it also compresses everything else. Light becomes trapped. Particles accumulate. Cosmic radiation piles up at the leading edge like snow collecting in front of a bulldozer. The faster the bubble moves, the more energy accumulates. Imagine driving through a rainstorm. Tiny raindrops strike your windshield. Now imagine driving faster and faster until every raindrop feels like a bullet. The warp bubble creates a similar effect, but on a cosmic scale. For what could be years of external travel, the front of the bubble continuously gathers enormous amounts of energy. At first glance, that may not sound catastrophic. After all, the radiation remains outside the spacecraft. But then comes the truly terrifying part. Eventually, the bubble has to stop. The instant the warp field collapses, every photon, every cosmic ray, and every particle trapped at the front of the bubble is suddenly released. Not gradually, instantly. Like opening the floodgates of a dam that has been holding back unimaginable pressure. Some theoretical studies suggest the resulting burst could carry enough energy to sterilize an entire planetary surface. Imagine arriving triumphantly at an alien civilization after humanity's first successful faster-than-light voyage, only to destroy the very world you came to explore. Your arrival becomes a weapon. Not because you intended it, but because physics made it unavoidable. Scientists began referring to this as one of the most dangerous side effects of the Alcubierre drive. Even if the passengers survived, everything waiting at their destination might not. The deeper researchers investigated, the clearer the pattern became. Every solution seemed to introduce another impossible consequence. Fix one problem. 3 more appeared. Then came another question that cut even deeper. Suppose we somehow solved every engineering challenge. Suppose we found unlimited negative energy. Suppose we stabilized the bubble. Suppose we learned how to steer it safely. Would the universe itself even permit such a machine to exist? Because modern physics contains another theory, one even stranger than general relativity. A theory that governs the smallest scales of reality. A theory where empty space is never truly empty, where particles constantly flicker into existence, and where certainty itself disappears. Quantum mechanics. And when quantum physics finally entered the warp drive conversation, the dream began to unravel in ways almost no one had expected. Quantum mechanics has a reputation for being strange. In fact, calling it strange may be the greatest understatement in all of science. This is the theory that tells us particles can behave like waves, that empty space is never truly empty, that uncertainty isn't a limitation of our instruments, but a fundamental property of reality itself. For over a century, quantum mechanics has passed every experimental test with astonishing precision. Its predictions have built the modern world, from semiconductors and lasers to MRI scanners and quantum computers. So when quantum physicists started examining warp drives, everyone paid attention. Because history has taught scientists one important lesson: whenever general relativity and quantum mechanics disagree, quantum mechanics usually exposes problems hidden beneath the surface. The Alcubierre warp drive was no exception. At first glance, the warp bubble appears perfectly smooth. Space contracts in front. Space expands behind. The spacecraft remains comfortably suspended inside a region of nearly flat spacetime. It almost looks peaceful. But according to quantum field theory, appearances can be incredibly deceptive. Even what we call empty space is alive with invisible activity. At every moment, countless quantum fields fluctuate throughout the universe. Virtual particles emerge from the vacuum. Matter and antimatter pairs appear together. A fraction of a second later, they annihilate one another, returning their borrowed energy to the vacuum before anyone could ever observe them directly. This isn't science fiction. It's one of the most experimentally verified predictions in modern physics. Normally, these fluctuations average themselves out. Space remains stable. But warp bubbles don't create normal space. They create regions where spacetime is bent to extraordinary extremes. And quantum fields respond to those distortions. Imagine stretching a rubber sheet. The more you stretch it, the greater the tension becomes. Now replace that rubber sheet with the quantum vacuum itself. The stronger the curvature becomes, the more violently quantum fluctuations react. Physicists eventually realized something deeply unsettling. The very act of creating a warp bubble might cause quantum energy to build up uncontrollably along its boundaries. Not slowly, not predictably, exponentially. Tiny fluctuations that normally disappear almost instantly could instead become amplified by the geometry of the bubble itself. The result would be something known as quantum back reaction. It's one of those phrases that sounds harmless until you understand what it means. The space-time geometry influences quantum fields. Those quantum fields then push back against space-time. Each affects the other, over and over again. Like placing a microphone too close to a loudspeaker. The microphone picks up sound. The speaker amplifies it. The microphone hears the amplified sound. The cycle repeats. Within moments, the entire system erupts into a deafening screech. Warp bubbles may suffer from an almost identical instability. Instead of sound growing louder, quantum energy grows stronger, until eventually it overwhelms the very geometry that created it. Some calculations suggest the energy density at the edge of the warp bubble would increase without limit. If that's correct, the bubble wouldn't merely become unstable. It could destroy itself almost the instant it formed. Imagine trying to inflate a balloon while microscopic explosions continuously erupt across its surface. No matter how carefully you inflate it, the balloon never survives. That's essentially what quantum mechanics appears to predict. Every attempt to stabilize the warp field generates new fluctuations. Those fluctuations destabilize the field even further, which generates even more fluctuations. A runaway process. An unavoidable feedback loop. This wasn't simply one research paper making an extraordinary claim. Over the years, independent teams working with different mathematical approaches arrived at remarkably similar conclusions. Again and again, quantum effects refused to cooperate. Researchers who initially believed warp drives might be physically possible gradually became far more cautious. Some openly admitted that the deeper they investigated, the less realistic the concept appeared. Others suggested that an undiscovered theory of quantum gravity might eventually rescue the idea. After all, modern physics remains incomplete. General relativity describes gravity beautifully. Quantum mechanics describes the microscopic universe with extraordinary accuracy. Yet the two theories still refuse to fit together perfectly. Somewhere beyond both theories lies a deeper understanding of reality. String theory, loop quantum gravity, or perhaps something entirely unknown. Until the theory is discovered, no physicist can honestly claim absolute certainty. But uncertainty cuts both ways. It doesn't prove warp drives are possible. It simply reminds us that our knowledge is incomplete. And based on everything we understand today, the evidence continues pointing in the same direction. Then another disturbing realization emerged. Suppose, somehow, quantum instability could be overcome. Suppose future physics revealed a method for stabilizing the warp bubble. Would humanity finally be free to travel faster than light? Surprisingly, not necessarily. Because there's another law woven into the fabric of the universe. One so fundamental that violating it threatens the very concept of cause and effect. Causality. Every event you've ever experienced follows this principle. A cause comes before its effect. Strike a match. Then the flame appears. Drop a glass. Then it shatters. The order never reverses. It sounds obvious because our entire experience of reality depends on it. But Einstein showed that space and time are not absolute. Observers moving relative to one another can disagree about the timing of distant events. Normally, this never creates contradictions because information cannot travel faster than light. That universal speed limit quietly protects causality. Remove that limit, and something extraordinary happens. Different observers can begin disagreeing not only about when events occur, but about which event happened first. Imagine sending a message that arrives before it was ever transmitted. It sounds absurd. Yet that's exactly the kind of paradox faster-than-light travel introduces into Einstein's universe. Physicists have demonstrated that sufficiently advanced warp drives could, at least mathematically, be arranged to create what are known as closed time-like curves. In simple terms, paths through spacetime that loop back into the past. A spacecraft following one of these trajectories might return before it ever departed. Immediately, impossible questions appear. What if you prevented your own launch? What if you warned your younger self never to build the warp drive? What happens if the cause eliminates its own effect? These aren't philosophical puzzles. They're mathematical contradictions. Nature appears deeply uncomfortable with them. That's why the famous physicist Stephen Hawking proposed what he called the chronology protection conjecture. His idea was elegantly simple. Perhaps the laws of physics themselves prevent time machines from ever forming. Not because someone forbids them, but because the universe becomes violently unstable before causality can be violated. Remarkably, several quantum calculations seem to support this possibility. As spacetime approaches the conditions necessary for time travel, quantum energy may grow without bound. Once again, reality appears to intervene, almost as though the universe has its own built-in defense mechanism. By now, a remarkable pattern has emerged. Every time physicists discover a possible route toward faster-than-light travel, another layer of physics quietly closes the door. First, energy requirements become impossible. Then steering becomes impossible. Then quantum mechanics destabilizes the bubble. Finally, causality itself threatens to collapse. It's almost as if nature isn't presenting us with one obstacle. It's presenting us with four independent warnings, all pointing toward exactly the same conclusion. And yet, despite everything you've heard so far, the story still isn't over. Because some physicists refuse to give up. Not because they ignore the evidence, but because science has a long history of surprising us when entirely new ideas emerge. The next chapter isn't about proving warp drives work. It's about asking whether we've been asking the wrong question all along. The remarkable thing about science is that it never asks us to stop dreaming. It simply asks us to dream responsibly. Again and again, history has shown that ideas once dismissed as impossible eventually became ordinary. Flying across oceans, landing on the moon, detecting gravitational waves, photographing a black hole. Each achievement seemed beyond reach until someone found a path forward. So why shouldn't warp drive follow the same story? It's a fair question. After all, every major breakthrough begins with someone challenging accepted limits. Perhaps future generations will discover new particles. Perhaps they'll uncover hidden dimensions. Perhaps they'll finally unite general relativity with quantum mechanics into a complete theory of quantum gravity. Could that theory reveal a loophole we've missed? Every honest physicist must answer the same way. Possibly. Science never claims absolute certainty. It only follows the evidence available today. And today's evidence tells a very different story from the optimistic headlines that often appear online. Over the last 3 decades, dozens of researchers have attempted to rescue the Alcubierre warp drive. Some proposed modifying the original geometry. Others searched for ways to reduce the impossible energy requirements. Several teams redesigned the shape of the warp bubble, hoping to eliminate the enormous quantities of negative energy demanded by the first calculations. For a while, each new paper generated excitement. Perhaps this was finally the breakthrough. Perhaps someone had discovered the missing piece. But every improvement came with its own cost. Reducing the energy requirement often made the bubble unstable. Stabilizing the geometry introduced new quantum instabilities. Removing one mathematical difficulty usually revealed another hidden beneath it. It became a pattern that physicists know all too well. Every answer created another question. Some researchers even explored whether ordinary positive energy might somehow replace exotic negative energy. The idea sounded promising. If successful, it would eliminate one of the biggest objections to warp drive. But once again, reality refused to cooperate. The mathematics continued pointing back toward exotic matter. Negative energy wasn't merely convenient. It appeared fundamental to the entire concept. Others wondered whether microscopic warp bubbles could exist naturally. Perhaps they wouldn't transport spacecraft. Perhaps they would appear only at the quantum scale. Tiny distortions in spacetime lasting less than a trillionth of a second. If such effects existed, they might reveal entirely new physics. So far, however, no experiment has found convincing evidence that nature creates anything resembling a usable warp bubble. That doesn't mean scientists have stopped searching. Quite the opposite. Modern physics thrives on exploring impossible ideas. Not because researchers expect every idea to succeed, but because even failed ideas often teach us something profound about the universe. Warp drive has already done exactly that. It forced physicists to examine Einstein's equations from entirely new perspectives. It inspired deeper investigations into quantum field theory. It encouraged new research into exotic matter, vacuum energy, and the nature of spacetime itself. Even if humanity never builds a warp engine, the pursuit has expanded our understanding of reality. In science, that's never considered failure. Sometimes proving that something cannot exist is just as important as proving that it can. But suppose, for a moment, we ignore every warning. Suppose an unimaginably advanced civilization somehow constructs a functioning warp drive anyway. What kind of civilization would be capable of such a feat? Certainly not one limited by today's technology. It would require energy sources beyond anything we've ever imagined. Control over spacetime itself. Mastery of quantum fields. materials unlike anything found on Earth. Perhaps even an understanding of physics that makes our current theories seem as primitive as ancient astronomy. In other words, a civilization so advanced that Arthur C. Clarke's famous observation begins to feel almost literal. Any sufficiently advanced technology is indistinguishable from magic. But even magical-looking technology must still obey the laws of nature. That's the crucial distinction. A smartphone would appear miraculous to someone living 1,000 years ago. Yet every component inside it follows ordinary physics. No natural law is violated. The same principle applies to warp drive. If one day humanity discovers a method for crossing the stars rapidly, it almost certainly won't look exactly like the Alcubierre drive described in textbooks today. History rarely rewards our first ideas. The Wright brothers didn't build modern jetliners. The first computers looked nothing like today's devices. Early rockets bear little resemblance to spacecraft exploring the outer solar system. Perhaps warp drive is simply our first rough sketch of a future technology. Or perhaps it's something even more valuable. A thought experiment. A mathematical lantern illuminating the boundaries of reality. Sometimes, the greatest discoveries don't come from finding new possibilities. They come from discovering where nature draws the line. And few ideas have revealed those boundaries more dramatically than warp drive. Every major obstacle we've explored points toward the same lesson. The speed of light is more than just a number. It isn't merely a limit on velocity. It appears woven into the deepest structure of space and time. Break that limit, and energy becomes impossible. Break it, and quantum fields rebel. Break it, and causality begins to unravel. Again and again, the universe seems to whisper the same message. There are no shortcuts. That realization can feel disappointing, especially if you spent years dreaming about starships crossing the galaxy. But perhaps we've been measuring progress the wrong way. Maybe the goal isn't to outrun light. Maybe the goal is to understand the universe so completely that entirely new possibilities reveal themselves. After all, our ancestors once believed the stars were tiny lights attached to a crystal sphere surrounding Earth. Today, we know they are distant suns, many with planets of their own. That transformation didn't happen because the universe changed. It happened because our understanding changed. The next revolution may arrive the same way. Not through faster engines. Not through impossible energy. But through deeper knowledge. Perhaps quantum gravity will reveal hidden aspects of spacetime. Perhaps extra dimensions exist beyond our perception. Perhaps entirely new principles remain waiting to be discovered. Science leaves room for those possibilities. What it doesn't leave room for is wishful thinking disguised as evidence. And that's an important distinction in an age where extraordinary claims spread faster than facts. You'll often see headlines declaring that NASA has built a warp drive, or that scientists have finally broken Einstein's speed limit, or that faster-than-light travel is only a few years away. Those stories attract millions of views because they appeal to something deeply human: hope, curiosity, wonder. But real science advances differently. Not through sensational announcements. Through careful measurements, independent verification, relentless skepticism, years of mathematical scrutiny. The truth is usually quieter than the headlines. Yet it's almost always more fascinating. Because the real universe doesn't need exaggeration. Its genuine mysteries are already extraordinary enough. And perhaps that's the greatest lesson warp drive has given us. Not that humanity will never reach the stars, but that understanding reality is far more challenging and far more beautiful than simply imagining it. Every equation we've explored, every obstacle we've encountered, and every unanswered question reminds us of one simple truth. The universe owes us nothing. It doesn't bend to our dreams. It doesn't rewrite its laws because we wish them away. Instead, it invites us to learn. to question, to explore, and sometimes to accept that the most profound discoveries are not about proving ourselves right, but about discovering how astonishing reality truly is. The universe has always rewarded curiosity. Long before we understood gravity, our ancestors looked into the night sky and imagined gods pulling the stars across the heavens. Long before we understood electricity, lightning was considered supernatural. Long before Einstein, space and time seemed fixed, eternal, and completely separate. Every generation believes it has reached the edge of knowledge. Every generation eventually discovers that the horizon was only an illusion. That's why science never tells us to stop asking impossible questions. It tells us to ask better ones. The dream of warp drive may never become reality, but that dream has already achieved something extraordinary. It forced humanity to question the deepest assumptions about the universe. What is space? What is time? Why is there a universal speed limit? Can space-time itself become a technology? These questions continue driving some of the most important research in modern physics. And regardless of whether warp drives are ever built, the answers may reshape our understanding of existence itself. Perhaps the greatest mistake we can make is believing that exploration only begins once we leave Earth. In reality, exploration begins with understanding. Every telescope we build, every particle accelerator we construct, every equation written on a physicist's chalkboard, each one is another step into the unknown. We often imagine that becoming an interstellar civilization depends on building a faster engine. But history suggests something different. Progress has rarely come from making existing ideas slightly better. It comes from discovering entirely new ways of thinking. When Newton described gravity, he transformed humanity's understanding of motion. When Maxwell unified electricity and magnetism, he changed civilization forever. When Einstein revealed that gravity is the curvature of space-time, reality itself became stranger than anyone had imagined. None of those revolutions were improvements. They were complete shifts in perspective. Perhaps the next great revolution will arrive the same way. Not by perfecting warp drive, but by so did the expanding universe. Every major breakthrough begins as an idea that seems impossible. The difference is that truly revolutionary ideas survive relentless testing. They survive mathematics. They survive experiments. Most importantly, they survive reality. That's the standard every scientific idea must eventually meet. Warp drive has not yet met that standard. And after decades of careful research, the evidence has only become more challenging. The energy requirements remain beyond imagination. Negative energy remains largely theoretical. Quantum effects appear destructive. Causality itself stands in opposition. These aren't engineering problems waiting for larger machines. They're warnings emerging independently from nearly every corner of modern physics. Could future discoveries overturn everything we've discussed? Absolutely. Science has surprised us before. It will surprise us again. But genuine scientific progress never begins by ignoring inconvenient evidence. It begins by confronting it honestly. That's why physicists continue studying impossible ideas. Not because they expect every dream to come true, but because every impossible question teaches us something about what is possible. Sometimes the greatest discovery isn't finding a new doorway. It's discovering why the old one was locked. And perhaps that's the true legacy of the Alcubierre warp drive. It reminded us that imagination has no limits. But reality does. Understanding those limits doesn't weaken our curiosity. It sharpens it. Because once we know where nature draws the line, we can begin searching for entirely new paths that no one has considered before. Maybe the future of interstellar travel won't involve bending space-time. Maybe it will involve generation ships carrying thousands of people across centuries. Maybe advances in suspended animation will make journeys that seem impossible today entirely practical. Maybe self-replicating robotic probes will spread through the galaxy long before humans do. Maybe quantum communication will connect civilizations without requiring anyone to travel faster than light. Or perhaps the universe has possibilities we've never even imagined. That's the beauty of science. It never closes the book. It simply turns the page. Every answer reveals another mystery. Every discovery uncovers another question. The universe remains infinitely more creative than our expectations. When we look at the stars, it's tempting to see barriers. Light years, distance, time, isolation. But perhaps those aren't walls. Perhaps they're invitations. Invitations to become smarter, more patient, more creative, more determined. The stars aren't challenging our technology. They're challenging our understanding. And maybe that's exactly how it should be. Because the journey toward the stars has never really been about reaching another planet. It's about discovering who we become while trying. Every generation inherits questions that seem impossible. Some spend their lives proving those questions wrong. Others discover entirely new questions that no one had ever thought to ask. That's how knowledge grows. Not in giant leaps, but through countless moments of curiosity. So, will warp drive ever work? Based on everything modern physics tells us today? Probably not. Not because humanity lacks intelligence. Not because we lack courage. But because the universe appears to have woven the speed of light into the very fabric of reality. And every attempt to bypass that limit uncovers another profound obstacle. Yet somehow, that conclusion doesn't make the universe smaller. It makes it infinitely more fascinating. Because if reality is capable of saying no so consistently, then understanding why becomes one of the greatest scientific adventures imaginable. The most extraordinary discoveries are rarely the ones we expect. Sometimes they emerge from failed experiments. Sometimes from impossible ideas. Sometimes from questions that seemed absurd when they were first asked. Warp drive may ultimately become one of those ideas. Not remembered as the invention that carried humanity to distant galaxies, but remembered as the question that forced us to understand spacetime more deeply than ever before. And perhaps that's an even greater achievement, because civilizations are not defined by how fast they travel. They're defined by how deeply they understand the universe they inhabit. The next time you step outside on a clear night, look up. Every point of light represents a destination that challenges our imagination. Not because it's unreachable, but because it reminds us how much remains unknown. Somewhere among those countless stars are answers to questions we haven't even learned to ask. Whether we reach them with warp drives, generation ships, or technologies beyond our current imagination doesn't matter nearly as much as one simple fact. We will keep asking. We will keep exploring. We will keep learning. Because curiosity is the one force in the universe that has never recognized a speed limit. And perhaps that has always been humanity's greatest engine.